Afternoon, everyone. So this is our start of a new unit, which is called chemical analysis. And today we're going to be looking at the idea of pure substances and mixtures. Now this unit is relatively short. We'll have done it in a couple of lessons, really, which is great news. Obviously, it doesn't take too long to get through it. There's not huge amounts of content in it. And it builds on a load of the information that we have learned already. So today is all going to be looking at the idea of pure substances and how we identify them and how we can do that using melting and boiling points, which hopefully is something that you would remember from your cooling curve kind of work or your heating curve work. And then we're also going to look at what a formulation is and about some examples of them and about how we can identify them. So we're going to start off with looking at what a pure substance is. So we've got two images here of pure substances, and this is the key bit to get across. A pure substance doesn't necessarily need to just be made up of one type of atom. Of course, that definition would be an element. A pure substance is where we have one type of element or compound and it is not mixed with any other substance. So over here in the images we can see that we've got some gold, we've got gold element atom particles kind of joined together, so that's an element, but we'd also say it's pure because there are only gold particles here. Down here we've got sodium chloride, and sodium and the chloride are joined together, so they're a compound. So it's pure because it's only got sodium chloride in it, despite there being two different types of atom that is making that substance up. So the overall idea is that you can't simplify this substance any more physically, so you can't separate it out any further. So example of this would be begin to think about water. So glass of water will contain molecules of H2O, as we can see up in the image here, those classic Mickey Mouse particles. Now, because it only contains particles of H2O, then we could talk about that being pure. So then we can consider this situation a glass of salt water, where we've got those water particles, but we've also got sodium chloride mixed in there as well. So is salt water a pure substance? So hopefully you should be able to identify the idea that salt water is of course an impure substance because there is more than one substance in there. And getting back to that idea of we can physically simplify it, we can remove the salt easily. We could evaporate the water and we'd be left with the salt, or we could distill it, and so this is an impure substance. So here is an activity for us to have a look at. We've got 5 images here. Each of the images are showing a pure substance or a mixture. So I'd like you to decide which is which. So pause the video, make that decision. Okay, so hopefully you'll have picked up the fact that we've got the grey one's pure substance, because you can see there's only grey atoms in here. This one that's diatomic. It's of course pure substance because it's got the 2 red particles in here. We've got a mixture as being our last picture on that top row because it's made up of both the red and the grey atoms. Pure substance, first picture on this bottom row on the left hand side because that's like CO2. And then final picture, bottom right, is of course a mixture. So another activity for you to pause and to have a look at. So what we're going to do is work through each of these. So you can see the question. I'll give a brief pause, read the question and decide which one is the odd one out. So 3 of these are pure substances, which one's the mixture? So there, hopefully you identified the fact that is of course D, because it will be a mixture of salts and water. So this one, we've got 3 mixtures again, but one's a pure substance. So which in that list would you consider to be the pure substance? So hopefully you should have identified vegetable oil there. You could argue about that, but generally it's made from oils from vegetables, so we'll accept that as an answer. So this one, we've got 3 pure substances. Which one's a mixture? So here, hopefully you identified the fact that it would of course be gravel. Next one, 3 pure substances, one is a mixture. Which one? Hopefully you identified, of course, that that would be chicken soup. 3 of these substances are pure, one is a mixture. So which one? Hopefully here you of course identified air, because it's a mixture of all of them. So here is a good list of a number of different pure substances and a number of different mixtures for us to consider. So we can identify pure substances using some very simple techniques. So if a substance isn't pure, that means that it's got impurities. And so what we want to think about is about how we can identify whether a substance has impurities. And we can do that by looking at boiling point and melting point data. Because if there are impurities in a substance, then generally the boiling point increases and the melting point decreases. So it changes the melting and boiling point of a substance. So when we look at the data, that can tell us whether a substance is pure or not. The other thing that we'll tend to notice about boiling and melting points is that they won't happen at specific points. They will happen more across a range as well, potentially, as we'll see in some of the following images. So a little bit of a thought here. So we've got a kettle boiling, we've got an ice cream melting down here. What happens when those substances change state? So pause and have a go at answering this question. This was of course a question on those November exams that we did, and it was a difficult one. So what you want to be thinking about is, of course, that the particles are going to gain kinetic energy, and if they are gaining kinetic energy, they're gaining that from the thermal energy that they are taking in, and what that means is that they will vibrate or they will move even more. That means that they gain that gained energy gives them enough energy to overcome the intermolecular forces that are holding them together, which means that the particles are able to separate. And so if the particles are able to separate, the state of the substance is able to change. So either the solid melts or the liquid turns into a gas. So harking back to some earlier work, here we can think about heating curves. And so for a pure substance, what we can see is that as time goes on, the temperature increases, and so we see that our temperature gets hotter, and of course those particles are going to vibrate more, and then it melts. And so we can see at that point the gradient of the graph is 0. So the melting happens at a specific point, so that indicates that it's a pure substance. Once the substance is fully melted, the temperature increases again of the liquid this time, and then we hit the next change of state, the boiling point. And so again, temperature doesn't change in this point because all of the energy that's being absorbed from the heat energy that's being put in is being used to overcome those intermolecular forces. And then once those forces are overcome, the substance has changed shape, and so it turns into a gas, and then the temperature can increase again. So for a pure substance, there are very precise, specific melting and boiling points. So have a go. Think about what labels you would put in each of those boxes for this cooling curve. The bottom ones will be changes of state. The top ones are names for the state of that substance. So what does the image show? So hopefully you identified, of course, that we've got a gas up here at the top, we've got a liquid down here, and then we've got a solid. So therefore here we've got the change of state where we're going from a gas to liquid, so we're condensing, and here we're going from a liquid to a solid, so of course we're freezing. So for impure substances, those heating curves will look slightly different because there will be no flat line. There will be instead a range over which the substance will melt or will boil or will freeze or will condense. So the graphs look very similar in that we have temperature increasing while it's in a particular state, but then the change of state, there is a much shallower gradient. And so that shallower gradient, the fact that it's not zero, tells us that the substance is impure. So we can find out whether a substance is pure or not simply by heating it up and seeing what happens when it is changing state. So here's a question for us. What would a bigger range of boiling points increase? So if this change occurred over a greater distance, what would it tell us? Hopefully you will have picked up the fact that if it's a bigger range, it means that there are more impurities, so it's a more impure substance, and so it gives us some indication about the actual purity of the substance that we are melting or boiling. So we said that melting point was a little bit different because what we find is that the melting point actually decreases. So here we can see it represented within this diagram. So we've got pure water represented in the green line here, and so we can see that the melting point or the freezing point of our pure water is 0, whereas for this red line this is seawater, and so the graph looks very different. We don't have those areas of 0 gradient that we had before. In actual fact, what happens to the melting point for that water is that it occurs over a range, the change of state, but that melting point is lower. So for seawater, we would talk about this being minus 2.5 degrees C. So here is a table of data for us. So we've got substances A to E, and we've got some melting point data, and we've got some boiling point data. Hopefully pretty quickly you can be identifying some substances there that are pure and some substances that are impure, maybe substances which are more impure than others, and potentially you can even name one of the substances in that table. So first question is substance A pure? Second question, can you name substance A? Third question, which substance could be an impure form of A? And then which one is the most impure substance with your reasoning? So pause video, answer those questions. So A is definitely pure because there's no range. A could of course be water. The substance which could be an impure form of A would potentially be C because the melting point has gone down a little bit and the boiling point has gone up. And the impure substance would of course be E because it has got the biggest range for melting and boiling. So therefore it has the more impurities included within it. So final bit is talking about formulations. So a formulation is a special mixture and it's been designed by scientists in order to be a useful product. So these products are complex mixtures in which each of the chemical has a particular purpose. So each plays a specific role. When you're making a formulation, the mixture that is created has very carefully measured quantities. There's a very specific mixture to put together that has certain amounts of each component, and what that does is it means that that overall product will have the properties that are required. So some examples, and this probably makes it all a lot easier, would be things like fuels, cleaning agents, thinking about paints, medicines, alloys, fertilizers and food. So for example, aspirin is an example of a painkiller, so this would fit into our medicine category, and it's got the active ingredient, the aspirin, the salicylic acid, but it also has some other things that are mixed in with it, with things like colorants and flavors and different binders to make the overall tablet. So therefore we talk about that being a formulation. So here's just some examples for us to work to, so you don't particularly need notes on this bit, but paints, we've said, are an example of formulation. So they can be used for decoration, they can be used for stopping metal corroding, or they can be used to preserve wood or something like that. So paints have a number of different components within them. They have the pigments, which give us the colour, they have binders which hold the colours together, and then they have solvents which often dissolve the pigments, and they will also affect how thick the paint is. So some special paints, so we could think about enamel paint, or we could think about anti-mold paints or kitchen paints, something like that, will contain other chemicals in addition. So their formulations will be even more specific. So another example, again, don't need to know huge amounts about this, but it's to illustrate for us would be chocolate. So chocolate is a food, so it's an example of a formulation because it's got cocoa, milk, oil, and food additives that are mixed in there. And each of those will be performing a particular role. And different chocolates will have different mixtures, and manufacturers will, of course, protect their formulation very jealously. So the additives that are in there will do things like improve shelf life, they'll change its taste, they'll make it sweeter, and so they'll all be playing a specific role. So here's a question to consider. Formulations are designed for specific purposes, so therefore are there any downsides to formulations, or potentially to the ingredients that may end up in a formulation? So the obvious side, kind of downside is about the fact that some of those additives may have negative side effects, and there we particularly think about drugs. So, two activities for you to have a go at. So, are these substances pure, impure, or formulation? So we've got sodium chloride, lipstick, 2p coin, hand cream, allergy medicine, seawater, chewing gum, and hand cream. So pure, impure, or formulations. Pause video. So sodium chloride would of course be pure because it's salt. Lipstick is a formulation, so we've got a product there that's been designed for a purpose. 2p coin is of course an alloy, so then again that's a formulation because it's been designed for a specific purpose. Hand cream is also a formulation. Allergy medicine is also a formulation. Seawater we've of course identified as being impure. Chewing gum would be a formulation, and hand cream would also be a formulation. So final activity is having a look at these definitions and matching them up to the keyword, please. So pause video. So a mixture that's been designed as a useful product is of course formulation. Temperature at which a solid will melt will of course be melting point. Compounds or elements containing only one substance would be a pure substance. Mixture of two or more different elements or compounds is of course something that is impure, and then temperature at which a liquid boils and turns into a vapor would of course be boiling point. So you need to make sure that you've made some notes on pure substances and formulations, so you know what those substances are. You don't need any specific examples of formulations, and you also need to know about how you can identify whether a substance is pure or impure from its melting or boiling point data. Right, thanks a lot. Have a good day.